class, we want to talk about heat exchange. Heat is the exchange of thermal energy between system and the surrounding. That is how thermal energy is being exchanged, through heat. It occurs when the system and the surroundings have different temperature. Heat flows from matter with high temperature to matter with low temperature until both objects reach the same temperature. We call that thermal equilibrium. So when a system absorbs heat, its temperature increases. The increase in temperature is directly proportional to the amount of heat absorbed. So mathematically, we call it heat capacity, and you see it as C. So Q, that's heat, equals to heat capacity times change in temperature. Change in temperature, delta T, equals to final temperature minus initial temperature. So that is heat capacity. So when a system absorbs heat, its temperature increases. The increase in temperature is directly proportional to the amount of heat absorbed. So the proportionality constant is called heat capacity. That is how we calculate it. The heat capacity of an object depends on its mass. So 200 grams of water requires twice as much heat to raise its temperature by 1 degree Celsius as does 100 grams of water. So the heat capacity itself also depends on the mass. And it also depends on the type of material. It depends on the type of material. So for example, 1,000 joules of heat will raise the temperature of 100 grams of sand by 12 degrees Celsius, but only raise the temperature of 100 grams of water by 2.4 degrees Celsius. So it depends on the material also. It depends on the material. It depends on the material. We want to talk about specific capacity. Since the heat capacity depends on the material, so the specific capacity is the amount of heat energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. And this is how we write specific capacity. Heat capacity is just C, specific capacity is CS. Then I want to talk about molar heat capacity. Is the amount of heat energy required to raise the temperature of 1 mole of a substance by 1 degree Celsius. So you have this table here. You see their specific heat capacities. They're different. But look at it, if you notice, the elements, the metals, they have very small heat capacities. And these other compounds, ethanol, water you see is very high. The specific capacity. Water is very important, so we want to look at its specific capacity. The rather high heat capacity of water allows water to absorb a lot of heat energy without a large increase in its temperature. So the large amount of water absorbing heat from the air keeps beaches cool in the summer. So without water, the Earth's temperature would be about the same as that of Moon on the side that is facing the sun. And that temperature is about 0.7 degrees Celsius or 227 Fahrenheit. That's high. Nothing can survive there. So water is commonly used as a coolant because it can absorb a lot of heat and remove it from the important mechanical parts to keep them from overheating or even melting. It can also be used to transfer the heat to something else because it is a fluid. Because it is a fluid. Quantifying heat energy. The heat capacity of an object is proportional to its mass and specific capacity. So we can calculate the quantity of heat absorbed by an object if we know the mass, the specific capacity, and the temperature change. And that gives us this equation. Heat, which is Q, equals to mass times specific capacity times temperature change. So we have this equation. So you can really calculate the amount of heat that a substance, an object receives or releases if you know the steps. You know the mass, you know the specific heat, and you know the temperature change. So let's take an example. How much heat is absorbed by a copper penny with a mass of 3.10 grams, whose temperature rises from minus 8 degrees Celsius to 37 degrees Celsius? The specific capacity of copper is 0.385 joules per grams per Celsius. So let's see what is given to us in the equation. So we have T1 to be minus 8, T2 to be 37.0 degrees Celsius. Thus T1 is minus 8 degrees Celsius. T2 is 37 degrees Celsius. M is 3.1 gram. We want Q in joules. So that's our plan. So this is our equation that we're going to use. And this is the specific capacity. It's a constant, so we got it from the table. So that's our equation. So don't convert the temperature here to Kelvin. No, we are using it in degrees Celsius. So T2 minus T1, it gave 45 degrees Celsius. So our Q is the mass times specific capacity times change in temperature, which is 53.7. So that's the amount of energy absorbed by copper penny. Now we want to talk about PV work. Pressure volume work. Pressure volume work, we call it PV work. PV work is work that is the result of a volume change against the external pressure. So PV work is work that is the result of volume change against external pressure. When gases expand, change in volume is positive, but the system is doing work on the surrounding. So work is minus. As long as the internal pressure is kept constant. So minus W equals to external pressure times change in volume. So that our work now is minus P times delta V, change in volume. Please, let's note this conversion. So 101.3 joules equals to 1 atmosphere times liter. So that's how we convert joules to atmosphere and liter. So we have seen work, because when the gas is released, it does work in the surrounding. So the system releases the work. That's why the work is minus P change in volume. So let's try and take this example. If a balloon is inflated from 0.10 liters to 1.85 liters against external pressure of 1 atmosphere, how much work is done? How much work is done? So V1, V2, P is 1 atmosphere. We want W. We know that W is minus P dot change in volume. This is just our conversion, converting joules to liter atmosphere. So our V2 is 1.85 liters, our V1 is 0.1, so our volume, change in volume, is 1.75 liters. So we got this already. And our pressure is 1 atmosphere. So W is minus 1.75 times 1, which is atmosphere liter. We can convert it to joules. Let's convert it to joules. So minus 1.75 atmosphere times, use this as conversion factor. The answer is minus 177 joules. That's our answer. Let's take another example. A certain process results in a gas system releasing 6.83 kilojoules of energy. So the gas system is releasing energy. During the process, 15.8 kilocal of heat is absorbed by the system. So it releases the system and absorbs this. If the external pressure is kept constant at 1 atmosphere and the initial volume of the gas is 10.0 liters, what is the final volume of the gas? I'll read the question again. A certain process results in a gas system releasing 8.3 kilojoules of energy. So that's the overall energy released. But during the process, 15.8 kilocal of this heat is absorbed by the system. external pressure is kept constant at 1 atmosphere and the initial volume of the gas is 10. What is the final volume of the system? So this is the amount of energy released. This is the amount of heat absorbed by the system. So we don't have the work. Let's see what work is, then we get it, then we use it to find the volume. We need to know the amount of work it did in the surrounding. So it's the same question. So this is the internal energy, and this is the Q. This is the initial volume. This is the pressure. We want the final volume. That's what we want. And we can get it from work. We need to find the energy that was used to do work. Then from there, we can find the final volume. So Q, delta E, will find work. Then PV will find the volume. So we are going to see our equations. This is the relationship between heat and work. This is the relationship between work, volume, and pressure. This is the conversion we are going to use to convert 1 kilojoules to joules. This we are going to use to convert calories to joules. Then this we are going to use to convert joules to atmosphere liter. So those are what we are going to use as conversion factors. First of all, so these are the equations. So work, we are going to have internal energy minus Q will give us the work energy. Then work divided by minus P will give us our change in volume. Then from change in volume, we are going to find the final volume. So first of all, let's convert our kilojoules energy to joules. So this is our conversion factor. That's our joules. And this is our internal energy. This is delta E. Now we want to convert our Q, the heat absorbed, in joules. So kilojoules to kilocalories to calories, then to joules. So this is what we have. Plus 6.604 times 10 to the minus 4 joules. We got that already. Now we want to find W. We are going to use this equation to find W. We have our internal energy. We have our Q. Now we want to find W. So internal energy, we got it. This is in joules. Then minus plus the amount of heat absorbed. And this is our W in joules. 2.26 times 10 to the 3 joules. So we are going to convert this W to atmosphere liters. So we use this conversion factor, and this is our W. Minus 2.3 is supposed to be this. What is this? Okay. When you divide it, minus 2.3 atmosphere liters. So that's it. That's it. Use your calculator. Now we have our W. We want to find delta V. W over minus P will give us delta V. So when you do that, our delta V change in volume is 22.3 liters. And we know change in volume is final temperature, final volume minus initial volume. So delta V equals to volume final minus volume initial. So delta V plus V initial will give us V final. So we have minus, so we have 22.3 liters plus 10.0 liters equals to V final or V2. So this will be, I think, 2.3 liters. That is our V final. So that's the V final. So that's it. That's how we got that. V2 is delta V plus V1. And that will give us 32 liters. This is in two significant figures. In summary of energy exchange between system and surrounding. So exchange of heat energy equals to Q mass plus specific capacity times change in temperature. Exchange of work is minus P times change in volume. So our system Q equals to M times CS, specific capacity, times change in temperature. And our work is minus P times change in volume. So we'll stop here and continue with measuring internal energy by the use of calorimetry at constant volume. So that's what we are going to continue. Thank you.